Yes, we are live. Good morning, good afternoon, good evening, good day, mid of the week. Welcome to one more session to Cloud Launch and Learn. Basically, tonight we have a really a nice guest and a really a nice topic, which we will hear a lot of interesting stuff. That's the main stuff. So for tonight, we have Pratik. Welcome to the show. How are you,
Thank you.
mate?
Thank you. I'm good. How about you?
Yes, doing good, mate. Happy to have you on this show and happy to hear something new. I'm always saying, yeah, all the sessions basically are with some new presentation, new topics. It's always nice to hear and learn basically something new. Happy to have you. So now I will leave the stage up to you basically to give the presentation. For the audience that will watch now or later, feel free to add your questions in the comments. So after the session, if there is a questions, Pratik will answer on all your questions, people. So Pratik, make the
Yeah.
stage is yours.
Thank you. Thank you so much for the introduction,
Yeah.
Martin. Let me start. First of all, good morning, everyone, and thank you for joining in from around the world. It's October 8th, 2025, and I'm right here in Mountain View. We are at the heart of where the future of computing is being built. Today, I'm going to talk about one of the most significant engineering challenges of our time is architecting autonomy. As I mentioned, my name is Pratik, and for the next hour or so, we are going to deep dive into technical blueprint of building intelligent autonomous systems using a unified platform, Google Cloud. This isn't a high level marketing pitch, this is a talk for architects, principal engineers, for the people in the room who have to build, scale, and secure these complex systems. We will be discussing the critical interplay between the centralized power of Google Cloud, the absolute necessity of Edge AI, and the non negotiable requirement for robust data governance. These three pillars are not independent, they are tightly integrated triad that forms the foundation of trustworthy autonomous system. Our goal today is to move beyond the abstract into the concrete. We will look at specific Google Cloud services, architecture patterns, and reference implementations. We will talk how to manage fleets of devices running on the Google Distributed Cloud Edge and how to process petabytes of data with Dataflow and BigQuery and how to secure it all with VPC, service controls, and IAM. By the end of this session, you will have a clear, actionable blueprint for designing the next generation autonomous system on a platform built for this very purpose. Before we start, let me introduce myself. I have I have had a great privilege of leading a team focused on designing intelligent solution softwares that truly drive engineering productivity and innovations. My core expertise lies in AI product management at the intersection of user experience, system design, and scalable tooling, with a strong emphasis on multi-device platform and services ecosystem, from architecting cross-functional or cross-platform recommendation system to tackling the hidden cost of deploying the large-scale models on constrained devices. I bring a pragmatic approach, which is product first approach to solving today's AI challenge. I believe and I'm deeply passionate about building the tools and frameworks that not only accelerate the efficiency but also spark creativity. Right now, my work centers on driving the Gen AI power transformation across the devices and services, helping replatform large scale businesses for the next era of intelligent application. Let's get started to our topic. So, what are we really talking about when we say autonomy? Let's ground this the real world engineering into the real world engineering. We are no longer just building the request response applications. We are engineering systems with continuous high frequency perception decision actions loop that must operate at a planetary scale. Think about a systems that pioneers like Waymo operating right here on our local streets. When I'm not sure if everyone has heard about Waymo, but Waymo is the self-driving car which is being operated in and around the San Francisco area as well as other parts of the world. So while working with these, we what I would be explaining is we are architecting a vehicle to everything communication fabric where, let's say, the sub 20 millisecond latency isn't a goal for us. It's the hard safety requirement for collision avoidance. This isn't something you can solve with a traditional cloud round trip propagation. Look at the modern logistics. We are deploying warehouse robotics that involve coordinating thousands of agents, each a node in a complex distributed systems. And we are enabling the next generation supply chains that depend on a unified data and AI platform like Google Cloud to maintain the real world global consistent view of operations. This requires a platform that ingest, process, and analyze data from millions of endpoints simultaneously. The key takeaway here is that these systems are not just cloud hosted, these are hybrid spanning from the centralized cloud to the far edge. They are data incentive processes, uh, the processing streaming of unstructured sensor data, uh, and they are mission critical where failures can have significant real world consequences. This is the new frontier of the system design, and it demands a new set of architectural principles. Next. As an engineer, we know this brings immense technical challenges. Let's focus on three hurdles. First is constant trade-off between the performance and the constraint. We train a massive FP32 model, uh, basically a floating point model, where in Vertex AI, it's but it's useless if it can't run on an edge TPU within a 5-watt power budget. These forces us into a world of model quantization and hardware optimization co-design. So that's the first point. The second point is uh, scale and throughput. We are architecting a millions of concurrent pub-sub connections, streaming telemetry. This data must be ingested reliably and all constant effectively into the system like BigQuery that can handle petabyte scale activities or analytics without falling over. And finally, we must establish a robust security posture where, with system spanning trusted data centers, sorry, and the physically insecure edge. The traditional perimeter is dead. We must adopt the zero trust model. On Google Cloud, this means using VPC services control to build the cryptographic parameters around our data and using conditional IAM policies to ensure every single request is authenticated and authorized. In today's agenda, I will be outlining our strategic vision for building a truly intelligent and resilient technologies framework. Our approach is to build on three pillars of architecture. We begin with Google Cloud Plane for robust scale management. We then extend our capabilities to the network's edge with edge computing, ensuring low latency and real time processing. Trying this all together is a framework of centralized governance, which guarantees security and compliance across all operations. But the powerful architecture is only the beginning. The future is collaborative, which brings us to the second point where human AI teaming is important. We are pioneering systems where human expertise is augmented by the artificial intelligence, creating a partnership that drives the innovation and smarter decision making. Following this, we will dive into the details with technical deep dives where we will explore the specific implementations, significant specific implementations, and data flows that bring this vision to life. By integrating these three pillars, we are not just building the system, we are building the future. These are the five core principles that underpin our entire architecture. First, you will see how to architect autonomous system as a distributed state machines that must be synchronized across the Google Cloud and Edge continuum. This means thinking about things like eventually consistency and designing for network partitions from the start. Secondly, you will understand why edge computing with Google's GPU is non-negotiable. This isn't just reducing the latency, it's about the fundamental economics of bandwidth and the sheer impossibility of backhauling petabytes of raw data. We will show how hardware acceleration at the edge is the only path forward. Third, we will demonstrate that a centralized governance model using Dataflex and VPC service controls is the only way to manage the trust and security at scale. Manually, security reviews and policies simply cannot keep up with the complexity and the scale of this system. Fourth, you will learn that true observability in these distributed environments requires the integrated Google Cloud Operations Suite. We will show how propagating a single trace ID from the edge device through PubSub, Dataflow, and GKE microservices is the key to reducing your mean time to resolution from hours to minutes. And finally, we will make the case for why committing to Google Cloud's integrated ecosystem is critical. While open standards are important, the velocity, security, and operational efficiency gained from platform where every service is designed to work together provide an undeniable engineering advantage. All right, let's get into the blueprint. This is our reference architecture, a comprehensive design for building autonomous system on Google Cloud. I want you to see this is not a collection of logos, but as a logical layered system. At the top, we have cloud acting as the central control plane and the system of record. This is where we have heavy compute. We are using GKE or the microservices which we have, and or any other microservices which we have. for orchestrating our microservices and providing a consistent environment for development and production. Alongside, you will see Vertex AI, our unified ML platform, and of course, cloud storage and BigQuery, the cornerstones of our data strategies. At the bottom, we have the edge. This isn't just a single device, it's a fleet managed by Google Distributed Cloud Edge. This allows us to run containerized workloads and benefits from services like local load balancing and storage, all merged from the Google Cloud Console. And critically, these edge nodes are equipped with HTPU for hardware accelerated ML interface. Now, look at the connectors, where these are the arteries of our system. We use gRPC for low latency, strongly typed command and control communication. Think of the cloud telling an edge device to update its mission plan. For high volume asynchronous telemetry, we use PubSub, which provides globally scalable, durable buffer. And for bulk data transfer, like uploading cache sensor logs, we use storage transfer services. To ensure this all efficient, we standardize on protocol buffers for our structured data, giving us schema evolution and performance. And we rely on BigQuery's high optimized columnar storage for analytics. This architecture provides a clear separation of concerns while ensuring tight, secure integration. Let's zoom into the cloud tier. We refer the cloud storage as the system of synthesis. This is where we aggregate data from our entire fleet to derive insights, train next generation models, and manage the system globally. The foundation of this is our data cloud architecture. We use Google Cloud Storage as our data lake, providing virtually limitless, cost efficient storage. But the key technology here is Big Lake. Big Lake allows us to create tables over our data in cloud storage and manage access at a fine-grained row and column level, all while maintaining open data formats. It effectively decouples the storage from compute and governance, giving us immense flexibility. For machine learning, Vertex AI is our end-to-end platform. This is not just a Jupyter notebook service. We use it for distributed training of massive models on dedicated cloud TPUs, which are purpose-built for training large neural networks. The output of these training jobs is versioned and stored in the Vertex AI model registry, which integrates directly with our CI/CD pipelines. And finally, for the fleet management, we need a robust way to manage the state of every edge devices. Following the cloud IoT core migration path, we built this on top of PubSub messaging. Each device has its own topic for commands, and we use a backend service, perhaps running on Cloud Run or GKE to manage device state and orchestrate secure OTA updates. This architecture is scalable, resilient, and built on core Google infrastructure. Now let's talk why the edge is a hard physical constraint. Edge computing is not trend. It's a requirement dedicated by the laws of physics and economics. First, latency. A robotic control loop or a collision avoidance system often requires a decision in under 10 milliseconds. Even with Google Global Network, the speed of light dedicates that a round trip from the edge to the nearest cloud region and back will be at best 30 to 50 milliseconds, or likely more. This makes local on device AI an absolute necessity for real time applications. Second, the bandwidth. A single autonomous vehicle with full sensor suite like cameras, LiDAR, radar can generate over a terabyte of data per day. This is economically and technically infeasible to stream that volume of raw data to the cloud. The only viable solution is to process that data where it's created, performing interference and data transformation locally. This is where Google Distributed Cloud Edge comes in. It's not just about running a container on a device. The Google Distributed Cloud Edge extends the Google's infrastructure and services to the edge. This means we get a managed Kubernetes plane, local storage, and networking, all running on hardware that is purpose built for this environment. It gives our developers a consistent API surface, whether they are deploying to a central GKE cluster or the Google Distributed Cloud Edge node in a factory. So, what does the AI and ML stack look like on these edge devices? The key principle is the co-design of the model and the hardware. You cannot treat them as separate concerns. The workflow starts with TensorFlow, where we design our neural network. Once we have a trained model, we use the Edge TPU compiler. This is a critical step. The compiler takes our TensorFlow model and performs post-training full integer quantization. More importantly, it compiles the model's operation into the format that can be executed directly by the edge TPUs. A specialized matrix multiplication engine. This process is what unlocks the hardware's full potential, delivering maximum performance per watt. The compiled model is then executed by the TensorFlow runtime on the edge devices. The runtime is lightweight and optimized for low power devices. For non-ML logic, like the Kalman filters we use for sensor fusions, we package that code into the standard containers and deploy it on the GKE clusters running on our GDC edge node. This two-pronged approach gives us the best of the both worlds. We get the extreme performance of the edge TPU for our AI workloads and the flexibility of standard Kubernetes environment for all our other applications. It's a powerful and efficient combination, I would say. Sorry. Our governance is centralized, multi-layered trust fabric. We start with Google Cloud IAM using the conditional policies for attribute-based access control, like granting access only from a specific IP range. The next layer is the VPC service control, which creates a cryptographic data perimeter to prevent exfiltrations regardless of IAM permissions. At the data layer, the Dataplex provides a unified plane for discovering and governing data across cloud storage and BigQuery. Finally, we secure our software supply chain with binary authorization in GKE, which ensures only trusted signed containers images from the Google Cloud build pipeline are allowed to be deployed. This defense in-depth approach provides comprehensive automated governance. Let's trace the life of a single data point to see how these pillars work together. An event occurs at the edge. A sensor reading is packed into protobuf messages and published to the PubSub topic. PubSub acts as a global, scalable ingestion point. A streaming data flow job, which is wireless, auto-scaling, processing pipeline, is subscribed to this topic. It performs real-time transformation, enriching the data, filtering out the noise, and maybe running a simple anomaly detection model. The processed data is then returned to a table in Google Cloud Storage that is managed by BigLink. The moment this data lands, it's instantly available for two purposes. First, it can be queried directly in BigQuery by our data analyst for business intelligence. Second, it can be used as a new training input for our models in Vertex AI. Once a new model is trained and validated, the Vertex AI model registry versions it. This triggers a cloud build CI/CD pipeline. The pipeline retrieves the model, compiles it for the edge TPU, packages it into a new container image, signs it, and then securely deploys it to our fleet of Google Distributed Cloud Edge services. This entire process from data generation to model deployment is fully automated symbiotic loop. To achieve true autonomy, as an engineer, we must have a human AI collaboration. We do this with Vertex AI pipelines, which orchestrate our entire ML flow. We build in steps for human in the loop validation, where the pipeline pauses and sends a model riskiest prediction to the human expert for approval before deployment. We also build active learning loops. Each device can flag low confidence prediction, which are automatically sent back to the labeling queue. This ensures our experts spend their time on the most valuable data. Finally, we use Vertex AI's traffic splitting capabilities for canary rollouts, safely validating our new models on a small subset of our fleet before a full release. This is how we engineer safety and trust directly into our release processes. On Google Cloud, trust is an engineered property, not an abstract concept. We define it as a function of three technical components. Reliability. Reliability is achieved through rigorous ML ops in Vertex AI pipelines with automated model testing, data validation, and drift detection. Second, explainability. This is a first-class feature provided by the Vertex AI Explainable AI, ensuring we can trace any model's output back to the input features that influenced it. This is non-negotiable for debugging and fairness analysis. Finally, security is a verifiable, secure software supply chain using Google Build for isolated builds and binary authorization to ensure only cryptographically signed trusted artifacts are deployed. Let's talk about the black box problem because it's one of the biggest barrier of adopting AI in high stakes safety critical domains. We are using incredible, powerful, and complex models, deep neural networks, transformers, and so on. Their very complexity, which gives them the power, also makes them opaque. The path from input to output involves millions of parameters, making formal verification incredibly difficult. On a platform like Google Cloud, the opacity has profound consequences. If a model served with, if a model is served from a Vertex AI endpoint, which makes a bad decision, denying a loan, flagging a transaction as a fraudulent, or in our case, stopping a manufacturing line, we are faced with a critical problem. How do we perform a root cause analysis on it? How do we satisfy a regulator who demands to know why a decision was made? How do we debug the model to prevent the same error from happening again? Without a technical solution for explainability, we are flying blind. This creates risk, erodes trust with users and operators. And ultimately, it prevents us from deploying AI and very application where it could provide the most value. This is not just a data science problem, it is a system engineering problem that we must solve. So, how do we solve it? We open the black box directly with Vertex AI Explainable AI. This is fully integrated managed service within the Vertex AI platform. It's not a separate tool you have to bolt on. It's a part of the core product. Vertex AI Explainable AI provides features like attributes for our models. It supports a variety of industry standard methods. For example, it can use sample shapely computational efficient approximation of the game theoretics values to assign a contribution score to each feature. For deep learning models, it supports methods like integrated gradients or XRAI, which are specifically designed to attribute predictions to pixels and in an image or tokens in a text sequence. The most important part is the integration. Explainability is not an afterthought that you run in a notebook. It is configurable options that you can enable when you deploy your model to a Vertex AI endpoint. You upload your model in the deployment configuration. You specify the explanation method you want to use. From that point on, every prediction request that to that endpoint can also return a detailed explanation. This makes explainability a seamless, operationalized part of our production ML services. Let's dive deeper into reality of the edge. We must design for the environment as it is, a high latency, low bandwidth, and zero trust zone. Network connectivity is unreliable with high jitters and frequent partitions. Your application must be designed to function offline. Compute resources are heavily constrained in power and memory, and the security model must assume physical tampering is possible. This is why hardware level security feature is secure boot and remote attestation, which Google's Edge ecosystem supports, are not optional. They are foundational requirement to establish a root of trust for your software stack before it even executes. To handle these constraints, our most important architecture pattern is aggressive data minimization. This means the processing data at the source and edge native cloud, edge native like extract, transform, load pattern. Instead of streaming raw multi megabyte video frames, the edge device runs a detection model locally, then it transmits only the resulting metadata, a tiny 1 kilobyte, maybe JSON object. If and only if something of interest is detected, as a code shows, this simple change reduces our data payload by a factor of 2000. It dramatically reduces cost, which makes our applications resilient to poor connectivity and significantly enhances user privacy. To enforce governance, we use a centralized multi-layered architecture. It starts with Cloud IAM, inherited through the resource hierarchy, setting broad security guardrails. The next layer is VPC service control, which creates a cryptographic data parameter around our project to prevent data exfiltration, acting as a critical backdrop to IAM. Within these parameters, Dataplex applies data-centric quality rules and access policies. This layered approach ensures that governance is consistently applied from the organization level down to the individual dataset, all managed centrally but enforced automatically across the distributed system. So here is our unified reference architecture one last time. It shows that holistic system where the strategic Google Cloud Control Plane empowers tactical edge devices. Now you can use how the critical cross-cutting corners are layered in. The VPC service control perimeter for security, the cloud operations suite for observability, Dataplex for data governance, and Vertex AI MLOps feedback loops for trust. This is complete blueprint for the resilient, observable, and governable autonomous system built on a single integrated platform. As we conclude, let's summarize the 5 core architecture principles we have discussed. These are the key takeaways that should guide your design of an autonomous system on Google Cloud. First, you must architect for distributed, state-driven world. Network failure is a default, not an exception. Your design must be resilient from ground up, leveraging services like PubSub for asynchronous messaging or Firestore for globally consistent state management. Secondly, recognize that the edge is non-negotiable. Physics and economics makes it hard requirement. This means treating hardware acceleration with the edge TPU as a first class component of our system, and it's the only way to achieve real-time AI within a constrained powered budget. Third, governance must be foundational to build trust. Don't bolt it on at the end. The only scalable approach is centralized, multi-layer strategy that combines the inherited policies of Cloud IAM, the cryptographic parameters of VPC service controls, and the data-centric rules of Dataplex. Fourth, navigate complexity with integrated observability. The true power of Cloud Operations Suite is its ability to automatically correlate traces, logs, and metrics. This integration is your key advantage, turning hours of debugging guesswork into minutes-long deterministic investigation. Finally, embrace the integrated platform. The engineering velocity and security you gain from services like Google Cloud feeding into the binary authorization for GKE is a decisive advantage. Together, these 5 principles, designing for distribution, leveraging the edge, embedding governance, demanding observability, and using an integrated platform to form a powerful and complete blueprint for building the future of autonomy. Thank you.
Well, except wow, I don't know what else to say, mate. I must be honest, it was a really wonderful presentation, first of all. And I immediately have 2 questions, by the way. And
Yep.
I will start with the first one because I saw the audience is shining a little bit. So, where do you see, if I may ask, the biggest bottleneck, if I may call it like that, today? Is it in the data quality, governance, latency, or me coming from CISO side, is it trust basically? Where do you see as a bottleneck from these 5 things, if I may say like that?
Oh, that's a good question. Uh, in my case, I would say like the major bottleneck is the data
Okay.
itself, and also not only data, I would say it's the trust. Also, we need to, is it the right data you're looking at? Because
Okay.
there are many models running simultaneously
Okay.
and it can overlap. So we need to have this edge, yeah, I mean, edge devices to
Yeah.
collect those analysis correctly and perform those analysis correctly, because the models might change significantly and the data might vary accordingly also. So those
Indeed, and
two, I
that
would say.
makes sense to be the trust basically as the first, and maybe the data quality, as you said, basically as the
Yes.
second. Fully agree. Okay, okay. My second question is, because you shared a lot of things, in my view, and really nice things, that how it can be done, this, and all of that stuff. But from the whole journey or your experience, mate, if I'm asked, where do you see all of this, let's call it like that, or how do you see the balance between the centralized and the localized, centralized cloud and the localized edge decision making? Because this will evolve in the next 3, 5, 10 years. We don't know, let's call it like that. But where do you see, if I may call it, the balance between everything we have in the cloud but also we have on the localized edge decision, if I may call it like that? Or do you
Um,
think there will be a balance about these two things? So we know that it's completely east and west, let's call it like that, because one
yeah.
is in the cloud, the other one is down. Is there a balance or something? We in CISO usually say man in the middle, is there something
Yeah.
man in the middle or something that will?
So my point would be like the four key factors
Okay.
while finding the balance is latency, computational demand,
Okay.
the data volume and bandwidth, and data analytics. Those
Okay.
are the four key parameters, I would say, because
Okay.
when you determine the balance, you need to have these specific requirements and approaches. And to make a decision for either AI or human in the loop with AI, you
Yeah.
need to have these parameters as the inputs where you can decide on making it more efficient or scalable or responsive to the ecosystem. So those are
Okay.
the four key parameters, I would say. Yeah.
Okay. Okay. Yeah, thank you. Yeah, I was really curious about the first because I have seen and discussed for this similar topics, let's call it like that, with colleagues, friends, and all that stuff. So I was really curious because you see really touch upon some very important points, let's call it like that, and all the stuff. So that's why I was curious about that. Yeah, I don't see any questions. I suppose the audience is quite shy. So here, yeah, I ask my questions, if I may be honest with you,
Yeah.
which I was curious about. Thank you for the honest answers. And yeah, I would like to thank you for the wonderful presentation, mate. I really enjoyed, to be honest. I hope the people that are watching and the people that will watch later, they will enjoy
Yeah.
also. And yeah, thanks to you, and thanks for everyone watching about. So yeah, for the audience or the people that will watch later this video, yeah, there is every week some session on the cloud launch and learn. So please take a look on the schedule on YouTube, and yeah, watch something and learn something new. Pratik, mate, thank you one more time. Have a nice
Thank you
rest
so
of the
much.
day, and have a nice rest of the day, all of you. Bye
Thank
bye.
you so much for having me. Bye.
Thank
Thanks.
you.